Um, all right. Well, hey everyone. Unfortunately, well, I don't get to see your faces, but great to know. Great to know that you're there. So welcome to the second part of this module on electronic excitations and Green's functions. Um, yeah, I'm still Johannes Lischner. Um, so let's see what this module is trying to do. Last week, we talked about basically trying to motivate GW in a non-technical way, basically trying to understand, why there is a need for theories beyond GW. And we introduced the concept of a Green's function, and we'll review that in a second a bit more. And the program for this week is then to learn about these Feynman diagrams, and also to learn a little bit about how GW actually works, in a practical numerical calculations. So I'll start with a review of well what we did a week ago, and we motivated everything. Basically by saying that there's a problem in DFT. Basically, when you interpret these cone-sham energies that you get out of a DFT calculation as quasi-particle energies, and we define the quasi-particle energy to be a total energy difference between an n-electron ground state and an excited state with one extra or one less electrons, which is precisely what is measured in a photo emission experiment, for example. So if you interpret cone-sham energies as quasi-particle energies, there's a problem, because when you compare these cone-sham band gaps to experimentally measured band gaps, there's a severe underestimate, at least when you use simple functionals such as the local density approximation. And in some sense, that's not so surprising, because these cone-sham energies are, not really meaningful. They're sort of a mathematical trick that allows us to basically construct accurate functionals. Now we're then basically, to get a little inspired about where we might find a better theory, we're looking at Hartree-Fock, and what we noted was that for molecules, actually the orbital energies that you get out of a Hartree-Fock calculation are in pretty good agreement with the experimentally measured quasi-particle energies. But actually for solids, Hartree-Fock is also not a good theory. While DFT underestimates the band gaps, Hartree-Fock quite dramatically overestimates the band gaps. So that can't be the ultimate solution. And but we were then thinking about what's missing in Hartree-Fock, or what's maybe different in a solid compared to a molecule. And the key insight is that basically in a solid you have a lot of other electrons. So if you consider the interaction between two electrons, that interaction is modified by the presence of all other electrons. And of course, in a solid, there are many more other electrons than in a molecule. And so what we hypothesized then is that the Coulomb interaction that enters the Fock exchange potential must be replaced by a screen interaction, where you essentially divide the bare interaction by a dielectric function, and that dielectric function must be energy dependent. And this led us then to GW theory, where you replace the exchange correlation potential of DFT with a so-called self energy, which is an energy dependent potential. And if you correct, and basically what this equation tells you is that you can correct the cone-sham energies of DFT using the difference of the GW self energy and the DFT exchange correlation potential to give you the actual quasi-particle energy that you can then compare to photo emission experiments. And I also showed you how this GW energy, self energy looks like. So the first term here is basically just a screened exchange potential. But there's another term, and that was the so-called Coulomb-Hole contribution, which is basically the potential that that the induced density creates that acts on the electron. So basically, the presence of the electron induces a charge density, and that charge density acts back on the electron. So sometimes this is described as a hole that the electron digs for itself. So this is how it looks like. But basically what we want to develop now is a theory that allows us to derive this expression, right? So right now we don't know where this self energy is actually coming from. And to understand where that's coming from, we had to introduce this concept of a Green's function. And I had to start telling you about Green's function theory. Now we defined the Green's function using this expression, which looks a little bit complicated, but basically what it describes is the propagation of an extra electron or an extra hole through the material, which is an interacting many electron system. So basically what this expression says is you either insert a hole at a particular space-time point, and then you move it at some point later, or you add an electron at a given space-time point and you remove it at a little while later. And so this is the object, the Green's function, that I propose to study. And the reason why this object is worth studying, we revealed a little later by sort of analyzing the Green's function as a function of frequency. So we did a Fourier transform from time to frequency. And when we neglect electron-electron interactions, we could just work out what this looks like. And basically what we saw is that as a function of frequency, the non-interacting Green's function has poles at the cone-sham energies, which basically correspond to the energy differences between the n and the n plus minus one, n plus n, which basically correspond to the quasi-particle energies if you don't have interactions. And a very similar expression could be derived when you actually include electron-electron interactions. Basically, what we could show that the exact quasi-particle energies are in fact the poles of the interacting Green's function, but the problem was that we didn't know how to calculate these quantities, right? So we don't know how to calculate epsilon n plus 1 lambda or epsilon n minus 1 lambda. And at that point we said we have to sort of make some approximation, and a reasonable starting point was to do try to develop a sort of perturbation theory in the interaction. And we also basically tried to understand how that could be done. So the interacting Green's function can be written down in terms of in this way, where basically you get a lot of these exponentials with the interacting Hamiltonian in the exponent. And basically we can express that Hamiltonian as a non-interacting bit and a bit that contains the electron-electron interaction. The non-interacting Green's function we can calculate, so we can handle the system without interaction, and then we simply do a Taylor expansion in the interaction Hamiltonian, and as you can see, that will generate a lot of terms that we then need to evaluate. In principle, each of these terms, is relatively straightforward to evaluate, but the problem is organizing all of these terms and that's where I told you these Feynman diagrams come in. So we'll start with looking at these Feynman diagrams. Anyway, so that was just a review of what happened last week. Are there any questions at this point? All right, if there are no questions, then we'll jump into basically how to construct these Feynman diagrams. Which are essentially a graphical representation of the various expectation values that you generate when you do this perturbation theory in the interaction. So let's first look at the ingredients. So we represent the Green's function by this line that has an arrow in it. So this is a line that goes from r t space-time point to r prime t prime. So that represents the interacting Green's function. And to represent the non-interacting Green's function, we just use a single line. And then finally, the only other ingredient is the interaction, which in our case is just the Coulomb interaction. We'll express that as a function of r and r prime and also t and t prime. But of course, the Coulomb interaction acts instantaneously, so this is just proportional to a delta function in the two time arguments. But if you have a retarded interaction, like the screen interaction, then of course you have some more complicated time dependence. And we'll draw this by a wiggly line like this that connects RT and R prime T prime. Right? So these are the three ingredients, and basically what we want to do is we want to express the interacting Green's function in terms of the non-interacting one and the interaction. Now, the way you think about it is basically, that the Coulomb interaction is mediated by photons, right? You can think of two charges interacting. You can think of this process as sort of the emission and absorption of photons. And this is a very useful picture when you draw these diagrams, because you can think of basically these electrons propagating, and once in a while they will emit a photon, and at some point later they will reabsorb a photon, for example. So let's then go through these rules for constructing a diagrammatic representation of the interacting Green's function. All right, so step one is basically to draw all topologically distinct connected diagrams with a certain number of Green's function lines and interaction lines. And I'll tell you what all these words mean. So we start by drawing all topologically distinct connected diagrams. So they're all in one piece. They're you can draw them without ever sort of, your pencil should never leave the paper. So that's what connected means. With a certain number of interaction lines, right? So n starts at 0, which means this is the same as the non-interacting theory, and then you have 1, 2, and then you have diagrams with 1, 2, 3, and so on, interaction lines. And then when you have n interaction lines, you will always need 2n plus 1 G0 lines. Right. So let me show you an example. So we want to represent the interacting Green's function, right, like that. Now, again, I'll draw from RT to R prime T prime, and of course, without interactions, the interacting Green's function is the same as the non-interacting one, right? So that's not a surprise. And now I want to draw. So this is basically the case where I have 0 interaction lines and 1 G0 lines. Then the next higher order is where I have 1 interaction line, and that means I have to draw a diagram with 1 wiggly line and 2n plus 1 equals 3 G0 lines. So let's see. There's 2 types. There's 2 such diagrams that I can draw. So the one looks like this, where you have basically the electron propagating. At some point, it emits a photon, keeps propagating, and then it reabsorbs the photon. And that's the end of it, right? So that is basically an n equals 1 diagram. But there's another one which looks like this. So you have, you start at RT, then you emit a photon, but the photon actually creates a electron hole pair, which is represented by this bubble, while the original photon keeps propagating to the position R prime T prime, right? So this is a diagram that has, 1 interaction line and 3 Green's function lines. So these are the lowest order diagrams in the interaction, n equals 1. Let me also draw the n equals 2 diagrams, and let me say, let me now go back to these rules. So in what sense are these topologically distinct, and in what sense are they connected? So as I said, connected means that, I can draw these diagrams without ever sort of my pencil leaving the paper. So they don't separate into 2 distinct pieces. And topologically distinct means that I can take these diagrams and I can deform them in any way. I mean, and that doesn't change anything. So for example, if I take this interaction line here and I draw it at the bottom as opposed to the top, that's topologically the same, right? So this is not a separate diagram. So so these are the lowest order ones. Now let's also draw the ones with 2 interaction lines, and there's quite a number of them. So let's see. So we could have something like this, where the electron propagates, creates an electron hole pair, which then sort of annihilates, and the photon is reabsorbed by the original electron. So that this one has 2 interaction lines and 5 Green's function lines, and that's an n equals 2 diagram. There's this one, electron propagates, emits a photon, reabsorbs it, emits another photon, reabsorbs it, right? There is the one where I have sort of this process, 2 times this process of creating this, emitting a photon, which creates an electron hole pair. And what else? I could have something like this, for example. I could have, right, so that's one. I could have something like this. I could have something like this. There's a couple more. I could have something like this. I could have something like this. And finally, I could have something like this. Right. So these are actually all the n equals 2 diagrams that you can construct. And you see, that's already quite a number. And the number of diagrams that you can construct grows relatively quickly with the number of interaction lines. Anyway, so this is the first step in this in this approach. So you first ask to draw all topologically distinct connected diagrams with n interaction lines and 2n plus 1 G0 lines. Okay, next step is we have to label each point where a G0 line meets an interaction line by a space-time point. Right, so let's see. So for example, here I have to put, and this is where they meet, right? So let's put R1, T1 here. This is another point, so let's call this R2, T2. Here I have R1, T1, I have R2, T2. Here I have R1, T1, R2, T2, R3, T3, R4, T4, right? And so on and so forth. So that's the second step. And then the third step is actually to write down an expression where we basically, which is a product of all these interaction lines and Green's function lines. And integrate over these RITIs. And then the final step is to multiply the expression by potentially with a minus sign. So we need to multiply by -1 to the f, with f being the number of closed G0 loops. Right, so for example, this diagram here has a closed G0 loop here. So this one has to multiply it by -1. This one has 2 closed G0 loops and therefore has to be multiplied by -1 squared, so by +1, while this one has no closed G0 loops. Right? All right, so let's put these rules into action and try to evaluate at least the n-1 diagrams. So how do these look like? So let's look at the n=1 diagrams. And well, just as a reminder, there's 2 of them, right? This one and this one. So we want to evaluate these 2 diagrams, and basically, well, we have to write down. Let's start with this one, I guess. So we have to write down this expression as a product of 1, 2, 3 Green's function and 1 interaction line, and we have to multiply this by +1, right? Because there's no closed loops. All right, so let's see how this looks like, and then of course we have to integrate over the internal variables. So we have, so let's first look at this guy here. Right, so basically I have to integrate over dr1, dt1, dr2, dt2, right? And then I have to write down this product. I have a Green's function that goes from r prime t prime to r2 t2. I have an interaction that goes from r2 t2 to r1 t1. I have another Green's function that goes from r2 t2 to r1 t1, and then I have another Green's function which goes from r1 t1 to rt. Right, so basically I've just written down as a product these 3 Green's function and 1 interaction, where I sort of just been careful to use basically precisely the right arguments, position and time arguments in these expressions, and then I integrate over the internal points. And well, I mean, you know what, and now you know what everything is, right? You know what G0 is, and you know what the interaction is. So in principle, this has now become an exercise in integration. Now, I don't want to actually work this out at this point. The only thing that I want to point out is when we take a look at these two objects here in the middle, basically, we can write this in the following way. We can write this as a sum over n, which is basically coming from the sum over n in G0, right? So if I I remind you that G0 can be written in this way as a sum over all the single particle states. So we have this a sum over n, and then we have our interaction. And I'm not writing the delta function in the times. And then I have these two wave functions in the numerator of the Green's function. So, so this object has a structure like this, which is a structure you already seen before, because this is precisely the Fock exchange potential. Right. So this emerges basically from an analysis of one of the n=2 diagrams, right? So this diagram here is basically closely related to the Fock exchange interaction. Now the other n=1 diagram was the one that looked like this, and we can go through the same kind of game. Now we have, this has one closed Green's function loop, so we need a minus sign. Need a -1, which is, well, we'll talk about it in a second. Then we again have to integrate over the intermediate times and positions. And then again, I have to write down this product of G0s and interactions. Let me just write this down. You can check it for yourself. R1, T1, V, R1, T1, R2, T2, another G0, R2, T2, R2, T2. So this is the Green's function that describes this closed bubble here, because it starts and ends at the same point. And then we have another one, R1, T1, RT. Right? So you can convince yourself that when you apply the rules, you get this expression. And again, now it's become an exercise in integration. Let me just point out that if you look at this bit here, you get an interesting structure, because well, let's first look at this one here. So when you look at this Green's function where both arguments are the same, basically what you get is a sum over n psi n r2 times psi n r2 dot, which is of course nothing but the electron density evaluated at R2. And so if I combine this with this position integration, and so if I combine these three things together, what I get is basically nothing but the Hartree potential. Right. So this is just your Hartree potential that enters, for example, your Kohn-Sham equation. So you see that these lowest order diagrams correspond to your Hartree interaction and your Fock exchange interaction, and it's good to know that there's this additional minus sign, because we know that Hartree and exchange have come in with opposite signs, such that Hartree-Fock is a self-interaction free theory. All right, so this is just how these Feynman diagrams work, and of course you see that as you go to these more and more higher order terms, these expressions get longer and longer and harder to evaluate. So we won't go into evaluating all of these diagrams, and there are people who do that, sort of just try to brute force it. Instead, what we'll do is we'll try to do something slightly more elegant, and we'll try to identify. We try to find some structure in this diagrammatic series, and it turns out there's a lot of structure to be found, in fact. So let's see if we can bring some structure, identify a structure of this diagrammatic series. All right. So basically, one thing that you will that's sort of very obvious when you look at all of these diagrams is that all of these diagrams have the same structure in some sense, and that's the following one, right? So all of these diagrams have an initial interaction line, right? So there's an initial G0 line. Then there is some stuff in the middle that involves the interaction, and then there's an outgoing G0 line. And each and every diagram, well, except for the first one, but other than the first one, each and every diagram has the structure, an incoming G0 line, something complicated involving interactions, and an outgoing G0 line. So all of these, so this allows us to write this whole diagrammatic expansion of the interacting Green's function in a very efficient way. Basically, it allows me to write it in terms of the non-interacting Green's function plus a diagram that looks like this. It has an incoming line. Then there's some complicated object that contains the interaction, and then there's an outgoing G0 line, right? And basically, this object that I defined here, which is basically called the self-energy, contains all the information about interactions. And so we can represent this self-energy, let's call it sigma tilde, diagrammatically. And basically what I need to do to represent this self-energy, I need to take each and every diagram except the first one and basically cut off the initial and the final G0 line. So that is not surprising. So so basically I can express this self-energy as a sum of diagrams which do not have incoming and outgoing Green's function lines, but instead sort of look like this. So I've just basically cut off these Green's function lines in all diagrams, right? Okay. So I've basically been able to, represent this infinite series in this very simple way, where of course I've just basically put all the complexity into this new object called the self-energy. And I can, of course, also express, I can use my Feynman rules to express this diagrammatic representation as an analytical equation. So what this says is just that G R prime T T prime is given by G0 R prime T T prime plus, and now I have to do my Feynman diagrams, right? I have to, I use my rules. I add some, I put some intermediate points, and then I integrate over those intermediate points. So I get something like dr1, dt1, dr2, dt2. Let me just erase some of this. And then I have a G0 from R and R1, T1. I've got my sigma tilde from R1, R2, T1, T2. And I've got another G0 R2, R prime, T2, T prime, right? So so this allows me to, I mean, this is just the analytical expression corresponding to this diagrammatic expression. All right, but there's more structure, and I can sort of identify this additional structure by taking a look at these Feynman diagrams for the self-energy. And basically, I can see that there are two classes. One class is basically the so-called reducible diagrams, and those are the ones that when you take a scissor and you cut a Green's function line, right? So I take a scissor and I cut a Green's function line, and then there are some diagrams that you can cut into two pieces, like this one or this one. And then there are some diagrams that you cannot cut into two pieces with a scissor if you cut a Green's function line, right? And so there's this fundamental distinction that some diagrams can be cut into two pieces when you cut a Green's function line, and some diagrams cannot, right? And this defines, so the ones that cannot be cut into two pieces are the so-called proper or irreducible self-energy diagrams. Well, those cannot be separated into two pieces by cutting a G0 line, right? Okay, so what does that mean? So that means that basically I can express my my self-energy sigma tilde in terms of another self-energy, basically a self-energy that only contains the irreducible diagrams in the following way. So this one is sigma, which only contains the irreducible diagrams, and you can express basically sigma tilde in terms of sigma in the following way. Right, and on, you know, by sort of repeating this, you generate all diagrams by sort of having these, by sort of, you know, putting these irreducible, by connecting these irreducible self-energies through G0 lines, you basically generate all the diagrams. Okay, so this is just another observation about the structure of the diagrammatic series. Now, what happens when I use this expression for sigma tilde and plug it into my diagrammatic expression for the self energy, for the Green's function, right? So I'm taking this diagrammatic equation and plugging it into this diagrammatic equation. So let's see what we find. So now we want to look at, I probably have to start a new page. So I have my expression for the Green's function. And well, there's a non-interacting Green's function. And now I basically replace sigma tilde by the sigma, and that generates an infinite series, of course, right? And on it goes, right? Now, what you see is, of course, that you can write this infinite series in the following way. Still have your G0, but you can see that, you know, you can write this infinite series in this way. Right, so I've just, well, if you sort of multiply these diagrams back together, if you multiply the second line back together, you generate the first line, right? But now if we look into this term in brackets, well, it's exactly the same as the first line. So the term in brackets is again the fully interacting Green's function. So what I can then do is I can express the interacting Green's function in terms of the non-interacting Green's function, and this diagram, which now involves the irreducible self-energy and the interacting Green's function, G, right? So the interacting Green's function is now both on the left-hand side and the right-hand side. All right. Now, we can again now express this diagrammatic equation as an analytic equation, and this is the famous Dyson equation. So what is it? Which basically says that the interacting Green's function is given by the non-interacting one plus, and now again I have to use my Feynman rules. I have to integrate over these intermediate points, R1, T1, R2, T2. So I have to integrate over those. And I have a G0, R1, T1. I have my irreducible self-energy sigma, R1, R2, T1, T2, and then I have my interacting Green's function G, R2, R prime, T2, T prime, right? So this is basically the Dyson equation, which we have discovered by, you know, revealing this interesting structure in the diagrammatic expansion of the Green's function. Okay, now how can we solve this equation? Well, I mean, the first thing to point out is that we're mostly interested in the Green's function as function of frequency, because the poles of that object give me the quasi-particle energies. So the first thing we'll do to this equation, we'll do a Fourier transform. From time to frequency. Next, we'll express all objects, basically the interacting Green's function, the non-interacting Green's function, and the self-energy in a basis of cone-sham orbitals. So what does that mean? So let's first look at G0. So I define, so I look at this expression where basically take sandwiching the Green's function between two Cohen-Sham orbitals. And prime, right? So this is basically going from a real space basis to a basis of Cohen-Sham orbitals. Now, of course, the Cohen-Sham orbitals are orthonormal. So what that means is that I only that this simplifies to a Kronecker delta omega minus epsilon n plus minus I eta. Right? So in other words, the non-interacting Green's function is diagonal in a basis of Cohen-Sham orbitals. Now, the self-energy is not necessarily diagonal in that basis, but it turns out that it's often a pretty good approximation to assume that this is the case. So so it's often okay to assume that also sigma is diagonal in this basis. So sigma nn prime omega is proportional to a Kronecker delta in the Cohen-Sham orbitals. All right, so if we do these two things, then basically Dyson's equation simplifies quite a lot, and we get the following. So it turns into a scalar equation right? Because basically, when I look at these time integrals up here, these are convolutions in time space. You remember that we proved that the Green's function doesn't depend on the two time arguments separately, but only on their difference. So these convolutions in time space turn into products in frequency space, and we get a very simple expression. Now we can simplify this even further by multiplying both sides. So here, so we'll multiply both sides by GNN inverse G naught NN inverse. So we multiply both sides by these, by the product of the two inverses, and rearrange things a little bit, and then we'll find our final expression, basically that the inverse of the interacting Green's function is given as the inverse of the non-interacting Green's function plus the matrix element of the self-energy, right? So this is our final equation. Again, it is based on the assumption of that the self-energy is a diagonal matrix in the Cohen-Sham orbitals, but as I said, very often that is a pretty good approximation. Let me just go a little further, and then we'll take a break. We said that we're looking for that. We said that the quasi-particle energies are the poles of the interacting Green's function, and the poles of the interacting Green's function are, of course, the zeros of the inverse of the interacting Green's function, right? So in other words, so the quasi-particle energies are the poles of G, and that means that that we can find the quasi-particle energies by searching for the zeros of the interacting Green's function. Right, so we'll set the left-hand side to 0, and we'll use that, and we'll use the fact that the inverse of the non-interacting Green's function is known analytically. It's just omega minus epsilon n. So what that means is then that the quasi-particle energies are given by this expression minus sigma nn e. All right, I'm calling it GW here. So, well, I guess I'm not quite consistent. Let me just call this the GW energies. Right. So, or in other words, if I rearrange this, then the GW energies are basically epsilon n plus sigma nn EGW. All right. Now, this equation looks very similar to the equation that we encountered last week. Where is it? Here. It looks very similar to this one. But they're not quite the same, right? So what's missing is this exchange correlation potential. And the reason is that so far we have assumed that, you know, the non-interacting Green's function really doesn't contain any interactions. But on the other hand, you know, in density functional theory does include some electron-electron interaction through Hartree and exchange. So we'll have to sort of put that in, the fact that, you know, these energies here are in fact not the DFT cone sham energies, but the true energies that you would get when you have no interactions whatsoever. So let's note this. So we assumed that G0 doesn't contain any electron-electron interactions. But of course, the DFT cone sham energies do. And how we can, okay, now we want to relate these two to each other. And for this, we first basically note that the self energy already contains a Hartree contribution, right? So we said that that when we look at this diagrammatic series, basically one of the n equals 1 diagrams describes the Hartree interaction. So we can write our self energy as an exchange correlation bit and a Hartree. So we can write our self energy as a Hartree potential plus an exchange correlation contribution, which contains all the other diagrams except the Hartree one. And then what we can do is the following. We can write our GW quasi-particle energy as epsilon n plus psi n sigma xc plus v Hartree. And now finally I can also add and subtract the exchange correlation potential. And well, if I combine the non-interacting energy with the Hartree and the exchange correlation potential, that's when of course, what gives me the DFT cone sham energy, and what remains is the difference of the exchange correlation self-energy minus the DFT exchange correlation potential. And now this is exactly the same expression that we wrote down last week. Okay, so that was all I wanted to say for now. I think it's a good time to take a 10-minute break. Are there any questions at this point? All right. If there are no questions, then, grab a coffee or whatever, and I'll see you at 2:10. Anybody has a question at this point?
Hi, yes, can I ask you a question?
Sure, go ahead.
Yeah, so well, many efforts have been devoted to include correlation in some way in DFT, standard DFT calculations, like, for example, DFT plus U approaches or hybrid functionals. So all those terms will also have to be subtracted from the self-energy in a GW approach.
No, because the only thing that's contained in so there are automatically all these exchange correlation, whatever exchange correlation potential you use, right? You subtract it out, right? So there's nothing you need to do, right? All you need to do is whatever fancy exchange correlation potential you use, you just have to subtract it out and replace it with the description of exchange correlation that GW offers you. So there's nothing complicated you need to do. The only thing that's sort of contained both in DFT and GW is the heart tree, right? So this is why we've sort of separated the self energy into a heart tree contribution and all the rest.
Okay, I see. I didn't know to what extent you had to be careful as to what you were subtracting with the exchange correlation, but it's simpler than I thought. Thank you.
Yeah. So that part is fairly easy.
Okay.
Okay, so let's continue. All right, so where were we? So we basically convinced ourselves that we can derive and that we can calculate quasi-particle energy by evaluating this equation where, as we just discussed, you start with the DFT calculation, you subtract out any exchange correlation that the DFT might contain, and you replace it with a description of exchange correlation that the self energy gives you, which is of course energy dependent, an energy dependent potential. Now, at this point, this is still the exact self energy, right? Which contains all diagrams that are basically, it contains all diagrams. Where were we? All self energy diagrams. So essentially diagrams where you have cut off the initial and the final G0 line, but only those diagrams which basically are irreducible, right? So this self energy contains all such diagrams here, and there's still an infinite number of these diagrams. So at this point, basically this equation is still exact. We haven't made any approximation yet. The only approximation that we have made here, in fact, is assuming that the self energy is diagonal in the in the cone sham orbitals, which for many material is an extremely good approximation. All right, so the next step is then obviously to figure out how to approximate these self energies. So we need to be able to calculate things, and that means we have to make approximations to the self energy. And I mean, one approximation is we've already basically encountered. We can write sigma, and if we only take the lowest order diagrams into account, which are these two, you see that both of these are irreducible, right? You cannot cut them into two by cutting a Green's function line. And these are the ones we evaluated a little while ago, and these are of course the Fock diagram and the heart tree diagram, right? So basically, if we only include these two diagrams, we get a heart tree fog. Of course, well, we want to do better than heart tree fog because we know heart tree fog isn't a good theory for band gaps and solids, and the reason is that it doesn't capture screening. So we need to understand how screening is represented diagrammatically. And that works as follows. So what you need to do, you need to sum an infinite series of diagrams. And basically, the other thing we know is that it's only the exchange that we should screen, right? So basically, we start with the exchange diagram, and now there is a set of other diagrams, higher order diagrams, that have a similar structure as the fog diagram. So let's look at it. So if you look, for example, at this diagram, where we have sort of a bubble, an electron hole bubble inserted into the interaction line, and we can repeat this process basically n number of times. So we can have 2 bubbles in the interaction line, 3 bubbles, and so on and so forth, right? On and on it goes. So we can basically insert these electron hole bubbles, so these are Green's function lines, into the interaction, and we can represent this as an effective diagram, which basically has a Green's function line and a screen interaction that will describe by this double wiggly line. So we'll define that this infinite series of diagrams is equal to this new effective diagram. And this new effective diagram, of course, looks exactly like the fog diagram, where I replace the bare interaction by a screen interaction, where this wiggly line is of course, so this double wiggly line is the screen interaction. So this is just a definition that we have made. Now let's see what this definition actually implies. So what we have said is that this double wiggly line is given by the single wiggly line plus the single wiggly line with these these Green's function bubbles inserted an arbitrary amount of times, right? And on it goes, right? So this is basically the equation for the Green's function for the screen interaction, and we see that this has a similar structure as the diagrammatic equation for the interacting Green's function. Basically, I can write it in the following way. Right? So if I multiply out these brackets in the second line, I get my first line back, but the expression in brackets is, of course, again, just the same as my screen interaction. And so I get an equation that's very similar to the Dyson equation for my screen interaction. Basically, I can write now this diagrammatic expression again as an algebraic equation. So my screen interaction is given by the bare interaction plus, again, I have to draw my intermediate points, right, like this, and integrate over them. So I've got like dr1, dt1, dr2, dt2. I've got my my bare interaction. Then I have this this object here in the middle. So this bubble here, which I will call chi0. So I will have an interaction. Then I have this chi0 object, And then I have another screen interaction. Right. So I'm just using these Feynman rules to translate my diagrammatic equation into an algebraic equation. And well, that's what it looks like. And basically, I can also, of course, evaluate the Feynman diagram for this chi0, and all that it is just G0 R1, let me see, R1 T1 R2 T2 times G0 R2 T2 R1 T1. So it's just the product of two Green's function that have sort of swapped arguments. So that's what your chi0 is. And this is, and basically, I mean, now you can evaluate this expression because you know what the Coulomb, you know what V is, and you know what G0 is, so you can figure out what chi0 is, and then solve this expression for the screen interaction. In practice, what you do is you again Fourier transform this equation from time to frequency space, and you work in a basis. Now, you could either work with a basis of Cohen-Sham orbitals, but you will find that this doesn't have such a nice structure as the equation for the Green's function, in the sense that these quantities are not diagonal in this Cohen-Sham basis. So often it's also represented in a basis of plane waves, for example. Anyway, so what we'll need to do, we'll need to Fourier transform plus choose a basis, and that will turn this equation into a matrix equation, which looks as follows. So we have our matrix for the screen interaction, which is equal to our matrix for the Baire interaction plus V chi0 omega. Right, so it's just we've just transformed this into a matrix product, and I can rearrange this. I can solve for the screen interaction, and it will look like this. I get a 1 minus V chi0 omega inverse times V. Right, so if I solve this equation for the screen interaction, I can write it in this way, and I can then define this to be an inverse dielectric matrix times the Baire interaction, and this is basically how you would normally define the screen interaction as a Baire interaction divided by some dielectric function. And now we can sort of calculate this dielectric function in terms of Coulomb interactions and Green's functions. Right. Okay. So let's take a step back. What have we done? So we have basically taken our Fock diagram, and we have replaced the Baire interaction in the Fock diagram by a screen interaction, right? And that corresponds to actually summing up an infinite series of diagrams. And so this one diagram actually represents an infinite number of diagrams. So far, what we have done is basically we've taken the standard Fock diagram and replaced the Baire interaction by a screen interaction, and you can actually take this one step further, and you can replace also the Baire Green's function by an interacting Green's function. So you have basically something like this. So you take the Fock diagram and you replace the bare interaction by a screen interaction. You also replace the bare Green's function by an interacting Green's function. And then this one diagram actually represents an infinite, actually two infinite series of diagrams. And basically this is the diagram that we try to evaluate in GW. So this is the GW Feynman diagram. Of course, replacing the non-interacting Green's function by the interacting Green's function causes some problems, because at the end of the day, the interacting Green's function is what we want to calculate, right? So we want to use the self energy to calculate the interacting Green's function. Now what I'm telling you is that the self energy depends on the interacting Green's function. So it's kind of like a chicken and egg problem, right? So we need to know the interacting Green's function to calculate the self energy, which then in turn allows us to calculate the interacting Green's function. And another way of phrasing this is that this introduces a self-consistency requirement. So the self-energy depends on the interacting Green's function G, which then basically means that we have to solve this Dyson equation self-consistently in practice. Self-consistency requirement. But let me also say immediately that in practice, this is quite rarely done. So in principle, you need to solve the Dyson equation self-consistency. In practice, this is very rarely done. Okay, so let's see. So we have now obtained our approximate GW self-energy diagram, and now we want to evaluate it. So let's see. So I want to use the Feynman rules to calculate, to evaluate this GW Feynman diagram. So what we are saying is that our GW self-energy, at least the sort of exchange correlation part of it, basically the part without the Hartree potential, is given by this diagram, right? And basically, well, the Feynman rules tell us that this diagram is just a product of G and W, right? So this is very easy. This is just G R R prime T T prime W R R prime T T prime, right? So this diagram is very easy to evaluate. And now, of course, what I want to have is I want to express everything in frequency space. So again, I want to do a Fourier transform to find the self-energy as a function of frequency. And since in real time it's a product, it becomes a convolution in frequency space, right? So it looks something like this. Let's see. So I want to use an E here. Sorry, this should be an E. 2 pi. I've got a G R R prime E minus E prime R R prime E prime. Right. So so you see it's a convolution in frequency or energy space. Okay, so this is this is what we need to evaluate, and this integral can be evaluated using the method of residues. where essentially we express this integral as a sum of contribution from the poles of the integrand. And we know that the Green's function has poles at the quasi-particle energies, but the screen interaction also can potentially have poles. So we need to be careful to pick up the poles from both G and W. Now, let's see, so let's write that down. Now, what's typically done, as I said, oftentimes people don't evaluate this self-energy self-consistently, but instead they invoke an additional approximation and say that we can approximate the interacting Green's function using the DFT Green's function. And the DFT Green's function is, of course, given by this expression where we use our DFT cone-sham orbitals in our DFT cone-sham energies. And in this expression, of course, it's very obvious where the poles are of the Green's function. And so I'm not going to take you through this integration in detail. I will just show you what you get. Basically, the GW self energy as a function of energy is then given by two terms, right? One term coming from the poles of the Green's function, and those will actually give you the screened Fock exchange. Right, so this is a screened Fock exchange, but there'll be an additional term which comes from the poles of the screen interaction, which you can express in the following way. So the second bit is what you get from the poles of the screen interaction. And this is, of course, looking a little bit complicated because you need to do this additional energy integral, which actually numerically is a bit of a pain. So often additional approximations are used to get rid of that integral. In the one type of approximation, you assume that E minus epsilon n is small. And in that case, you get something, the integral looks like this. But this is just, this can be related to the real part of the screen interaction using the Kramers-Kronig relation. And what you get is basically this thing. Right, so if you make this assumption, then this integral can be rewritten using the Kramers-Kronig. And the other thing that you can use is that this sum here can now be expressed as a delta function, right? Because of the completeness of your cone-sham states. And then basically the second part becomes the Coulomb hole self-energy that I've shown you last week. Right. So so that's one type of approximation. To be honest, this is not frequently used. So this approximation actually still overestimate band gaps quite a bit. A much more common approximation is where you use a so-called plasmon pole approximation. And the assumption that you make in the plasmon pole approximation is that the imaginary part of the screen interaction is proportional to a delta function, which is centered at the plasmon energy. And of course, if your imaginary part of the screen interaction is a delta function, that delta function immediately kills this energy integral. And so you've solved that problem as well. And so this plasmon pole those plasmon pole approximations you will quite frequently see. I mean, they're slowly disappearing because nowadays we are often, I mean, it's often possible to just evaluate this energy integral without additional approximation. But you know, even a couple of years back, most GW calculation would invoke a sort of plasmon pole model to simplify this energy integral. Okay, so so basically, I've now shown you how we can derive the GW self energy using this diagrammatic analysis. And the last bit is I want to just show you how you would go through a actual GW calculation. So if you want to sort of pick up a GW code and calculate, I don't know, a band gap or something like that. But are there any questions at this point? All right, if there are no questions, then we'll go on and come to the last bit, which is GW in practice. And basically, if you want to do a calc, if you want to pick up a code like, I don't know, Berkeley GW or Yambo, or maybe even VASP or something like that, this is how you would do it. Again, the calculation would involve several steps. Step one, typically you start with a DFT calculation. Could also be, you know, Hartree-Fock calculation, but most often it's DFT, where you need to calculate both the occupied cone-sham orbitals and the unoccupied and the empty ones. Right. And well, and then there's always the question, how many of the empty ones do you need? And you will see that this is a convergent parameters, and depending on the system, sometimes it can happen that you need actually thousands of empty states to converge your GW calculation. Then the second step is you construct the screen interaction. For this, you need to first evaluate this chi0. Basically, where is it? You need to evaluate this object here, right? Which we said is a product of two Green's function. Now I can express each of these Green's function in terms of sort of their, you know, in terms of their form, and this allows me then to do the frequency integration if I want to express chi r prime as a function of energy, and I get the following. So I get a sum over n and n prime, where n ranges over the occupied orbital and n prime ranges over the empty orbital, and I need to evaluate something that looks like this. So you have a product of two Green's function. Each Green's function contains two cone-sham orbitals. So you get something that involves four cone-sham orbitals and two cone-sham energies. And then there's another similar term. Right. So you first need to calculate this object. And the problem is, in this term here, you need to sum over all empty states. And you know, in practice, of course, you introduce a cutoff, after which you stop summing, and then basically this empty state cutoff is a convergence parameter in your calculation, and actually it's a very important one. So you can get a wide range of results if you don't properly converge these empty state summations. Once you have chi0, you can calculate epsilon, the dielectric function, which has now become a matrix, right? So we calculate epsilon, which is given by 1 minus v chi0, right? And of course, I need to express basically what I've done here. I have expressed chi0 and epsilon in a basis, and for example, something like plane wave. And again, how many of these plane waves I use to represent these quantities is another convergence parameter. So I express chi0 in a basis, e.g. plane waves. That's what Berkeley GW does. And the number of plane waves is again a convergence parameters. Unfortunately, so now we have identified two convergence parameters. One is the number of empty states in the summation up here, and the other one is the number of basis functions in the matrix representation of chi0. And unfortunately, it so happens that these two convergence parameters are actually not independent of each other. So you can't just keep one fixed and then converge the other one. You need to converge them both at the same time. And that makes convergence of these calculations a relatively tricky business. And sometimes you can get sort of false convergence, which is, of course, undesirable. Okay, so we've got epsilon, and then the last step is we need to construct the screen interaction, which is just the inverse of the epsilon matrix times the bare interaction. All right. But as we said, the frequency, the screen interaction is a function of frequency. So in principle, I need to evaluate the screen interaction on a frequency grid. And since this frequency and since the screen interaction can have poles, this means, unfortunately, that sometimes we need a very fine frequency grid to represent this function. So there's another problem. That we need this object on a fine frequency grid. As I said, there are alternatives. And that is to do a plasmon pole model. Basically to assume that the imaginary part of the screen interaction, which is needed for this integral up here, is a delta function. And so, in that case, of course, this dramatically simplifies things. And then the very last step is then to evaluate the self energy. Which is also not so trivial because the self energy involves another empty state summation here. So in the screened exchange term, we're only summing over the occupied states, but in the Coulomb hole term, we again have another summation over all states, both occupied and empty. So this happens twice. And so I need to evaluate the self energy, and then at the end of the day, I need to solve the equation for the quasi-particle energies. Which of course is also not so easy because of the self-consistency requirement that the quasi-particle energy and is both on the left and is also on an argument in the self energy. And finally, let me also point out that at this point we still have ignored this issue that in principle we have the self-consistency requirement for the Green's function, what we talked about here. So this is yet a separate issue that, as I said, is often simply ignored. Anyway, so you see that these GW calculations, they are a little bit involved, but nowadays these codes are also becoming quite mature. Berkeley GW, Yanbo, VASC. There's actually also a range of local orbital GW codes, for example, implementations in Turbomole or FHI AIMS. So there's actually quite a number of codes to pick from. And depending on what kind of codes you use, they sometimes take care of a lot of these convergence parameters for you. But of course, it's still something that you need to be aware of. Anyway, so that was all I wanted to tell you about, excited states, GW, self energies, Feynman diagrams, and all of that. Do you have any questions? Well, if there are no questions whatsoever, then that's the end of the module. I hope you learned something. I hope it was useful for you. If you want to give me feedback, feel free to shoot me an email. Or if you have any other questions, also feel free to contact me. And otherwise, thank you for listening. And I guess I hope you enjoy the rest of the course. Take care, everyone. Bye-bye.